Just before Newton was another scientist, Johannes Kepler. And both these guys lived about 400 to 500 years ago. Johannes Kepler was an astronomer, and he observed the planets, and he was meticulous in his observation. He came up with 3 laws. He observed that the planets orbited as ellipses. They weren't perfect circles. And he also observed that the sun was at one of the foci, that there are 2 focuses or foci. The sun is at one of them, and the planet orbited around that foci. He also said that if you draw a line from the sun to the planet, it will sweep out equal area in equal time. And his time was constant. It was the click, click, click of the second. And then his 3rd law related time, the orbital period, to the major axis. And again, the time was constant. So these are great scientists 400 to 500 years ago that developed very precise mathematical equations. And they worked. In fact, F equals ma and Kepler's laws work so well that we sent men to the moon and back with those laws alone. But in the early 1900s, a young patent clerk at the Swiss Patent and Trademark Office, you may have heard of him, Albert Einstein. He would sit around in his mundane job and do thought problems. And of course, as he commuted back and forth to the Patent and Trademark Office, he got on a train one time in Switzerland, and as the train sped away from downtown, he looked back at the clock tower and looked at the hands. And he thought to himself, what if this train went faster and faster and faster? What if it went the speed of light? What would those hands do? And in his mind, he realized that he was seeing light from those hands that reached his eyes, and that's how he was telling the time. And he postulated in his mind that if he were traveling at the speed of light, the light of the hands that he saw would be frozen in time. They wouldn't move because he was traveling at the speed of light. And in his mind, he said, I think that time changes with speed. And in 1905, he publishes a paper called Special Relativity. And he says that velocity alters time. Unheard of. That it's no longer fixed. It is not the click, click, click of the second hand. It's based on your speed. And he was right. But if you think that is unusual, 11 years later, in 1916, he extends the theory to something he calls general relativity. He says that gravity changes time. He says that gravity alters space and time, like the fabric of a trampoline. This is unbelievable. In fact, when he publishes the paper in 1916, most people think that he is off his rocker. There is no way this can be right. But as they go and begin to test the theory, general relativity may be the most tested theory that we have ever looked at. Nowhere have we ever found it wrong. And it has answered a number of gigantic questions in the universe. It does seem that mass alters space and time. It bends the fabric of space and time. Einstein also talks about something he calls the equivalence principle. He says that gravity is equivalent to inertial acceleration. Here's what I mean. Take the elevator back here where David is sitting. Ever been in an elevator? Well, of course we all have. When the door closes, there's no window. You are in that elevator. You don't know what's going on outside of you. And so in your reference frame inside that elevator, you don't know where you are or what's going on. If you were to take this clicker and let go of it, it would fall. So under Earth's gravity, Earth would accelerate this clicker down at 32 feet per second, which means that for every second that this falls, it gains velocity by 32 feet per second. You know, in the first foot, 32 feet per second. In the second foot, it's now going 64 feet per second, and it will just fall faster and faster and faster until it hits the floor. Einstein said, what if? Let's take that elevator and put it out in space where there's no gravity. You're just floating. But let's put a rocket motor on the bottom of the elevator, turn that motor on, and begin accelerating you, just like Newton talked about in F equals ma, acceleration equals force divided by mass. And let's turn up that rocket motor so it's accelerating at 32 feet per second. And now ask you to let go of this pointer and describe what happens. Well, it will fall to the floor of the elevator at 32 feet per second. In your reference frame, it is impossible to determine if you are in space being boosted by a rocket or if you're on the surface of the Earth being pulled down by gravity. And he says that they're equivalent. Now here's what's unusual. When you were driving here to the museum, did you cross the Paluxy River Bridge and then come around the corner kind of fast, and you feel yourself getting pulled to the outside of the turn? We call that centrifugal force, but it's not a real force at all. Is anything really pulling you to the outside of the turn? I mean, is there a rope attached to your waist going and trying to pull you out of the car? There's not. Centrifugal force is not a force. It's the result of the car turning out from under you. Now, centripetal force with a P is a real force, but not centrifugal. But I guarantee if you undo your seatbelt and open the door, you will fly out of the car. That's all that's holding you in that car. Einstein said gravity is the same thing. It's not a real force. He says that matter bends space and time. And we feel that as a pseudo force. It's like a trampoline. Picture the fabric of a trampoline that's smooth and flat. And then put a bowling ball in the center of the trampoline, and it will depress the fabric. And then on the outside of the trampoline, take a little marble and let go of it and watch it roll down on that fabric. Is there a force pulling that marble toward the bowling ball? No. The fabric slopes down and the marble starts to roll. So Einstein's equivalence principle is that gravity is the exact same thing. And so here what we feel sitting in your chair and me standing up is the fact that the Earth is altering space around us. And like that marble, we tend to want to fall toward the center of the mass. That is really, really peculiar. But here's what's way strange. Einstein says that not only does the Earth alter space, it changes time. They think he's crazy until they begin to investigate and experiment. And we find out that, in fact, it is true. Massive objects like the Earth or the Sun or a black hole alter time. They dilate it tremendously. So what that means is that the time down here, and if we look at our watches, in our reference frame, they are all clicking along second by second. They'd be perfectly synced in this room. But for somebody out in orbit around the Earth where the gravity is less, their clocks are running faster. Anybody see the movie Interstellar? Kind of a fun movie to watch. Well, there's a line in there that says, you know, on this planet, one day is 7 years on Earth. And you think, oh, that's just Hollywood fanciful thinking. It is not. That is exactly right. Remember, the premise of the show is they leave Earth to find a new world, and they somehow travel to Gargantua. That's a gigantic black hole. They're exploring a planet around this black hole, and that planet is so close to Gargantua, this gigantic black hole, that time is markedly different. In fact, it is slow, slow, slow on that planet. So slow that one day there is 7 years here. That is true science, by the way.